Hello, I would like to tell you about our new video quality metric, which can predict the quality for both standard and wide field of view video. I'm Rafał Mantiuk and I'm a reader at the University of Cambridge, and I'm presenting this work on behalf of my co-authors, Gyorgy, Alexandre, Chapiro, Anton, Kaplanyan, Gizem, Rufo, Romain, Bachy, Trisha, Lian, and Anjul, Patney. This work is a collaboration between Facebook Reality Labs and the University of Cambridge. Our goal was to create a metric for foveated video quality assessment, for example, to evaluate foveated rendering techniques. This means that we want a metric that is sensitive to temporal artifacts such as flicker, but also accounts for our gaze direction shown here with the cross. And this is because obviously distortions outside our gaze location are much less noticeable. Let me first explain why we need image and video quality metrics and why they are so important. Probably the most common use case is the evaluation of existing and newly proposed techniques. For example, any single image super resolution paper typically has this kind of table, which contains both PSNR and SSAM values for different techniques. Such a table is used to demonstrate that the proposed method is better than other techniques. Those metrics replace tedious subjective experiments, which require both time and expertise to run them well. The second important use case is in optimization. For example, we could come up with a new rendering algorithm that has a dozen of tunable parameters, and we want to find the best trade-off between the quality and the rendering time. Doing it manually for a dozen of parameters is difficult, so we would prefer to delegate such a task to a metric. The final and important application is a full reference metric for a loss in deep learning methods. For example, we may want to have something better than L2, L1, or VGG loss for training a new super resolution method. And for that, we need a difference metric that is fast, differentiable, and aligned with visual differences. The focus of our current paper is on points 1 and 2, and point 3 is on our roadmap, but is still a work in progress. There are hundreds of existing image and video quality metrics, so let me explain how a metric differs from them. The list of metrics on the slide is not exhaustive, but it shows representative examples of relevant classes of metrics. PSNR, SSAM, MSSAM are probably the most widely used image metrics, which, however, do not account for video, for foveated viewing, and they disregard display brightness and size. If we want to account for display physical properties, we need to switch to a physics-based perceptual metric such as HDR-VDP3, which, however, will not account for video perception or foveation. There's a group of metrics that model foveation, but they do not model any temporal aspects. And this is relevant because foveation is a dynamic temporal phenomenon. We have also video metrics, which model certain temporal aspects, but they ignore foveation. Finally, we have metrics that rely on deep learning, like LPIPS over here, and which are exceptionally accurate on datasets they were trained on. But they do not generalize well across the datasets, and they do not explicitly model any perceptual and physical aspects. Our metric accounts for temporal vision, foveation, physical display properties, and is based on psychophysical models. Our metric belongs to a class of visual difference predictors, which started 3 decades ago with the VDP by Scott Daly. I work on the HDR-VDP, which extended the original VDP to the domain of high dynamic range by accounting for glare and local adaptation. HDR-VDP2, which we released in 2011, improved many components of the first version predicted not only visibility but also quality, and was much better calibrated. We have released the code for HDR-VDP, although the paper is still in preparation. I call HDR-VDP 3 a multimetric because it has multiple prediction tasks, such as comparison of images shown side by side, comparison of images flickered between one another, quality prediction, and it's also a tone mapping metric. With FovVideoVDP, we took a different route. We added video foveation. We much simplified the metric and made it 100 times faster than HDR-VDP 3. We released both PyTorch and MATLAB code for the metric. However, because we wanted a simpler metric, we had to remove some components such as glare, orientation selectivity of the bands, cross-channel masking, and we focus on the predictions of quality rather than visibility. So what is a foveated video VDP? It is a white box visual difference metric that is built from psychophysical models. One of the main design goals was to make it as simple as possible, which is important if you want to process hundreds of video frames or use it as a loss function. So why did we not go a deep learning route, which is a common trend these days? This was because we wanted a metric that is explainable, has few parameters, and can be trained on small data sets, and additionally generalizes well to unseen data. And these are the features which unfortunately deep learning models still lack. The diagram below is a high-level overview of our metric. Without going into too much detail, we explain the main processing stages, and I will justify some of our decisions. The first stage of our metric is a display model. It's meant to account for the physical specification of the display, its size, resolution, viewing distance. If the metric is operating in foveated mode, we also need to know the fixation point. The display model accounts for the fact that pixel on a mobile phone is not the same thing as a pixel on a VR headset. And the metrics that ignore this fact cannot really generalize across different devices. In the next stage, we decompose the input image or video into two temporal channels, and then each of those we decompose into a number of spatial frequency bands. The first sustained channel acts as a low-pass filter and accounts for the finite integration time of the visual system. The second transient temporal channel acts as a bandpass filter and is sensitive to rapid temporal changes. For example, it's sensitive to flicker. When we sum up the frequency response of both channels, we get a shape which is similar to this spatio-temporal contrast sensitivity function. To decompose into spatial frequency bands, we use the Laplacian pyramid because it's simple, fast to compute, and we found it to provide sufficient isolation of the frequency bands. The core of the metric is the model of contrast sensitivity and masking. Without this part, the metric would be very inaccurate. We actually have tested a dozen different variations of masking and sensitivity models to choose the one that offered the best performance. The contrast sensitivity function tells us what's the smallest contrast that is visible to human eye. It is the function of luminance, eccentricity, but also spatial and temporal frequencies. There was no existing model that we could use. Therefore, what we did, we combined spatial velocity CSF from a 2006 paper by Lian and others with our own HDR CSF, with the ideas of cortical magnification from the paper of Wiltz and Rafał, and also with the ideas behind pyramid of visibility by Watson and Ahmada. So the CSF provides a perceptual scaling for the contrast masking model. And contrast masking tells us how well a particular contrast is camouflaged by another contrast. For example, the gabor shown in the first column is masked or camouflaged by a sign grating which increase in amplitude in each consecutive column, making the Gabor patch less and less visible. The final stage of our metric is perceptual scaling. First, we need to pool the visual differences from all spatial and temporal bands into a single visual difference value. And then we use our data sets to scale this value into the units of just objectionable differences, or we call them GODs. GODs are very important for a metric because they provide predictions in a well-defined unit. One GOD corresponds to a 50% increase in preference. Such a percentage is much more meaningful and useful unit than an arbitrary correlate of quality given by both metrics. So why do we predict GODs instead of directly predicting percentages? And the reason for that is that percentages saturate at one point, and they cannot encode suprathreshold differences, something that GOD units can do. Moreover, GOD give a useful absolute scale that starts at 10 for the perfect quality and decreases with the distortion. On the right, you can see an official criteria that my co-author came up with to give a meaning to GODs. So why do you use GOD units instead of better known just noticeable differences or JNDs? Both GOD and JNDs are very similar, but there's one key difference. JND is a relative perceived difference between any pair of images. So for example, if we have a blurry image and a noisy image, they may differ a lot between each other, and perhaps the difference between them is for JNDs. However, if you ask how much the quality is degraded in relation to a perfect reference image, the distortion level could be about the same. And GOD are meant to capture the visible difference in relation to the reference, and therefore two images of equivalent quality have the same GOD, even for they are many JNDs apart. We probably spent most of the time in this project on calibration, validation, and ablation studies. We use 4 datasets with over 400 videos and over 4,000 images, and most of the videos were foveated. The first dataset over here, which we call FovDots, was collected especially for the purpose of this paper. It was meant to measure the quality depending on sampling and filtering parameters, which are commonly used in foveated rendering. At first, we did what any other metric paper does. We split each data set into training and testing sets, and we could easily show that we outperform any other quality metric. But then we started testing the metric across the data sets. And what we found was that the predictions do not make sense. When trained on one data set, the predicted GOD values from another data set didn't really match the quality that we could see in images and video. This is because the correlation coefficients which are commonly used to measure how well a metric correlates with subjective judgments, they ignore the absolute quality scale. For that reason, we had to run an additional subjective experiment in which we match the quality of a condition in one data set to the quality of the condition in another dataset, so that we could scale all the datasets in the same GOD units. Then we trained to predict the absolute quality of all datasets at once, which was a much harder task, but gave us confidence in our predictions. The testing results show that our metric outperforms by a good margin the second best metric, which was VSI. The existing foveated metric FWQI did not perform very well and was outperformed by existing video and image quality metrics. The scatter plots on the right, they show how well metric predictions, which are shown on the x-axis, correspond to the subjective scores, which are shown on the y-axis. The closer we are to the diagonal, the more accurate are the predictions. What is worth noting is that for many metrics, the entire data sets are an outlier, which means that they can do a good job in terms of predictions within the dataset, but they do not generalize well enough for the cross-dataset predictions. In addition to a single GOD quality value per image, our metric can also generate visual difference maps. In this example, we are changing the magnitude of blur over the time, and the visualization on the right shows that the blur is the most visible in the portion of the image that contains high spatial frequencies. FovVideoVDP is fast. Here you can see the plot of processing time versus the image size, and FovVideoVDP is right at the bottom, with the fraction of the processing time of other metrics. However, this is set with a big asterisk, that our metric runs on a GPU, while other metrics are running on a CPU. But in practical terms, FovVideoVDP is 100 times faster than HDR-VDP3. We did not want to just show that the metric works well on a data set, but we really wanted to test the metric on practical and useful applications. In the first application, we predict how a low frame rate is causing video to appear juddery or non-smooth. This is based on the data from the paper by Chapiro and his colleagues, in which they pan an image at certain speeds and at certain luminance levels, and then measure the quality of that animation. The plots on the right show that the metric can predict the data quite well at 40 and 10 candela per square meter, and it over-predicts slightly at 2.5 candela per square meter. And this is most probably due to the limitation of our CSF. The second application was foveated sampling. Here we wanted to render video for VR and transmit over a wireless link. And to save on bandwidth, we want to use the largest sampling rate possible. We want to choose the sampling rate based on eccentricity, luminance, and contrast. So here our metric predicted that when we are looking at the pawn over here, the edges of the pawn need to be rendered at a higher resolution, but because the sky is mostly flat, we can render it at the lowest sampling rate. The final application I would like to mention is the subtle gaze direction. Here we want to introduce a flicker in the image, which would attract our attention and direct our gaze, but would be subtle enough not to affect the quality of the content. Ideally, we would like to select an amplitude of the flicker in such a way that is just noticeable. And this is something that can be predicted by our metric. In summary, we propose the first metric that accounts for video, foveation, contrast sensitivity, and contrast masking. This is an explainable white box metric that is built on well-established psychophysical models, and therefore we believe it should generalize well. The quality is provided in GOD units or percentage improvement in quality, which should be more meaningful than a mean opinion scores or dB values offered by other metrics. The metric is fast and we believe it's widely applicable. The PyTorch and MATLAB code of the metric is available under the URL shown over here. And thank you very much for listening.